So, our last piece of information is to discuss what would happen to improve the accuracy of these approximations or to recognize when these approximations might be a little bit of an overestimate or an underestimate in a similar way to the way we used tangent lines to estimate values nearby, and we had to determine if that estimate was over or under. So if we're going to improve your accuracy, your best bet is to continue to add more rectangles or trapezoids if the data allows you to add in more. The more rectangles and trapezoids you can have, the more accurate your estimation is going to be. In general, if you are limited with what you are able to use, a midpoint or a trapezoidal sum tend to be the more accurate approximations, although again, it very much depends on the data that is presented to you. Here we're going to illustrate kind of when our methods are going to over or underestimate. In here, we're going to draw each one of these rectangles and trapezoids on these two graphs. Something I want to point out is that your x-axis is along the bottom in both of these cases. So we are dealing with functions that have f of x as greater than or equal to 0 when we are kind of working with these rectangles and these approximations. So I'm going to go through and I'm going to draw in 4 left Riemann sum examples based on these two curves. And we're going to do 2 rectangles in each curve. So here in red, I have the 4 left Riemann sums that are spaced out between these two curves. What I want you to notice is the very first one, all the way over on the left, is an underestimate as to what the area would be for that particular space. The next one is an overestimate. The next one is also an overestimate. And the last one, it's difficult to see, but it would be an underestimate. So the two rectangles, the left rectangles that have an overestimate, are happening for these types of functions and these types of functions in terms of the way the function is curved and in which direction the function is heading. What I mean by that is that for both overestimates, the function is decreasing both times. The function is decreasing along this portion of the curve and then also decreasing along this portion of the curve. So when our function is decreasing, our left Riemann sum ends up being an overestimate. And think about what that means in terms of your x and y values. If the function is decreasing, the value on the left will be higher than the value that's on the right. And we're taking the left values to be the height of each rectangle. So we're going to end up with an overestimate for when f is decreasing. In a similar way, we're going to get an underestimate anytime f is increasing. So if we look here at our function, it's increasing along this portion. And again, we're increasing along this portion. And we have an underestimate in both cases. So when our function f is increasing, our left Riemann sum will end up being an underestimate. And again, think about what that means. The value that is on the left-hand side will be smaller than the value that is on the right-hand side. And so the rectangle will end up underestimating the total area under that curve. So we're going to repeat this process and we're going to take a look at what happens when we're dealing with a right Riemann sum. So here in green, we have a couple of right Riemann sums that we're working with. The very first one is an overestimate, then we have an underestimate, another underestimate, and another overestimate. And these all fall into that same pattern of whether or not the function is increasing or decreasing is going to dictate whether the right Riemann sum overestimates or underestimates. So a right Riemann sum will overestimate anytime the function is increasing and underestimate the total value under the curve when f is decreasing. Next up will be the midpoint Riemann sums. So here in purple, we're going to see the midpoint Riemann sums, and you can see that each one of them kind of overlaps and underlaps the function at any given point. So there isn't really a way to figure out when a midpoint sum is going to overestimate or underestimate. So unfortunately, that has no clear indication. Last up is going to be the trapezoids. I'm actually going to go through and erase a couple of these rectangles so we can get a better glimpse as to what the trapezoids are doing. So here are the trapezoids that we end up with by kind of making them a little bit larger so we can have an easier time to see if they're over or under approximating. In this case, over here on the left, they are both under approximations. And on the right, we have some over approximations. So it's not about whether or not the function is increasing or decreasing that causes these approximations to be over or under. It's all about the concavity of the graph. We're going to have an overestimate whenever the graph of f is going to be concave up. And what's happening is the secant line that gets formed between the 2 points that are on the value is actually sitting above the curve itself. The underestimate is going to happen whenever the graph of f is going to be concave down. And again, this is happening because when we pick those 2 points and create a secant line out of them, which basically represents one side of our trapezoid, that's going to end up being below the curve. So where this might be useful is if you're given a limited amount of data, but you're told or given extra information saying that the graph is going to be, say, concave up on the entire domain of your data, then we'll be able to approximate or give a reason as to why we think our approximation would be an over or underestimate. So we're going to have to look and investigate at what the data is in the actual table, and also if there are any clues in a prompt somewhere that indicates whether the f is increasing, decreasing, or concave up or concave down, to also improve upon our accuracy and know if our estimation is going to be over or under.